Students, in this session we will discuss the effect of PI controller in the control system. See, PI controller means proportional integral control, and in this case, in the case of proportional integral control, transfer function of the PI controller is given by GC of S equal to Kp into 1 plus 1 by TIS, where Kp is the proportional gain and Ti is the integral time. We can write it as Kp into Ti of S plus 1 divided by Ti of S. Usually, this proportional integral controller transfer function is given to the forward path of the control system. That means it is given in the open loop system. Open loop path, that means GC of S will be connected in series with the G of S, so that the overall gain of this path will be changed. The overall gain of this path, this forward path, is GC of S into G of S. Here is a block diagram of a unity feedback system with the PI controller, and in which forward path contains the transfer function of PI controller and the open loop gain, and the feedback path is a unity feedback path system. And in this case, the open loop transfer function G of S is given by omega n square divided by S into S plus 2 epsilon omega n. Now the loop transfer function can be obtained by the multiplication of GC of S and G of S with the feedback gain H of S. That is, here feedback path has got a feedback value H of S equal to 1. So we can write it as GC of S into G of S. Substituting the value of GC of S and G of S, we will get Kp into 1 plus TIS divided by TIS into, instead of G of S we can write omega n square divided by S into S plus 2 epsilon omega n. By multiplying the terms, we will get Kp omega n square into 1 plus TIS divided by S square Ti into S plus 2 epsilon omega n. Now we can write the closed loop transfer function as C of S divided by R of S, which is given by GC of S into G of S divided by 1 plus GC of S into G of S. So we can substitute for each and every quantity, and now we can cross multiply these terms and cancelling the denominator terms. So we will get Kp into omega n square into 1 plus Ti of S divided by S square Ti into S plus 2 epsilon omega n plus Kp omega n square into 1 plus Ti of S. In this case, we can multiply the terms with the terms inside the bracket. So we will get Kp omega n square into 1 plus Ti of S divided by TIS cube plus 2 epsilon omega n Ti into S square plus Kp omega n square Ti of S plus Kp omega n square. Here we can take the Ti from the denominator side outside, so that it will come to as Kp by Ti. Here Ti is taken from this term. So numerator terms will have omega n square into 1 plus Ti of S divided by, when taking Ti from this term, we will get S cube plus 2 epsilon omega n S square plus Kp omega n square S plus Kp by Ti into omega n square, where Ki equal to Kp by Ti, and it can be given as Ki into omega n square into 1 plus Ti of S divided by S cube plus 2 epsilon omega n S square plus Kp into omega n square S plus Ki into omega n square. So this is the closed loop transfer function when we introduce a PI controller in the forward path. Actually, we start from this point. Here you can see that this is the first open loop transfer function, and in this case you can see that there is no zeros for this function. Also, the order of the system is 2 and type number of the system is 1. Actually, order is the highest power of S, and the type number is the number of poles that is locating at the origin. Here the number of poles that is locating at the origin is 1, which is actually given by the power of S raised to terms, and here the order is the highest S raised to term. Here the total highest S raised to term is 2. So here the order is 2 and the type number is 1, and the number of zeros is equal to 0 here. But when we introduce a PI controller, you can see that the number of zeros has increased for this closed loop transfer function. Also, the order changed to 3. From 2 to 3, there is an increase in the order. Also, the type number has also a change for this case. Okay, see the type number, how the type number is changed. You can see here the type number is 1, but here the type number is 2, right? This is actually the transfer function, and the type number is changed to 2. So we can make such conclusion that from the closed loop transfer function, we can see that in the case of PI controller, there is a single zero in the system, and if we are if we are introducing a PI controller, the number of zeros is increases, and also the order of the system is increased by 1. So the increase in the order of the system results in the less stable system than the original one, because higher order systems are less stable than lower order systems. Similarly, PI controller increases the type number by 1, and the increase in the type number results in the reducing the steady state error. So these conclusions we can make from this analysis. Next, we will discuss about the effect of PD controller. You know that PD means proportional derivative controller, and here in this case the transfer function of the PD control is given by GC of S is equal to Kp into 1 plus Td into S, where Kp is the proportional gain and Td is the derivative time. And we can draw the block diagram of a unity feedback system with the PD controller, which is shown in the figure. The block diagram contains GC of S, which is in series with the G of S, and single feedback unit is feedback is 1. So this is shown in the figure. So we can make analysis. See, open loop transfer function is of this system is, first is G of S is equal to omega n square divided by S into S plus 2 epsilon omega n. When we introduce GC of S or PD controller, we can write the loop transfer function as GC of S into G of S into H of S. Here H of S is 1, so we can write it as GC of S into G of S. We can substitute the value of GC of S and G of S, so we will get Kp into omega n square into 1 plus TdS divided by S into S plus 2 epsilon omega n. So now we can find the closed loop transfer function as C of S divided by R of S, which has the equation GC of S into G of S divided by 1 plus G of S into GC of S. If we are substituting the values, and we will get the terms Kp into omega n square into 1 plus Td of S divided by S into S plus 2 epsilon omega n plus Kp into omega n square into 1 plus TdS. Here we can multiply the terms inside the bracket, so we will get the terms like this, and in this case you can take the S terms from this and this terms. S term can be taken outside, so we will get a Kp omega n square into 1 plus Td of S divided by S square plus 2 epsilon omega n plus Kp into omega n square Td of S plus Kp omega n square, which is equal to omega n square into Kp plus Kd of S divided by S square plus 2 epsilon omega n plus Kd omega n square of S plus Kp omega n square, where Kd equal to Kp into Td. See, in this case we can make the conclusion that in the case of PD controller, that is proportional derivative controller, which introduces a zero in the system, and also it increases the damping ratio. Here first there is no zeros in the transfer function, but when we are introducing a PD controller, it will increase the zero in the system. See, here you can see that the zero is introduced in this system, and also it increases the epsilon value, or it increases the damping ratio. So the addition of zero may increase the peak overshoot, but it reduces the rise time. And see here that there is an increase in the damping ratio. This damping ratio will ultimately reduces the peak overshoot. And also you can see that PD controller does not modify the type number of the system. So This is all about this controller topic, that is PD and PI controller. Thank you.